Good evening and welcome back to Vegas October 1 Sounds. Tonight we're going to take a little trip into the commercial world, and I'm going to present to you a review of some of the research to develop commercial systems for sniper localization. And actually I'm just going to review one system that's being developed in Europe under the guidance of the French and collaboration with some other folks. And this device, as you can see from this picture, is a head-worn helmet which can operate alone or can operate in conjunction with other nearby helmets. And so what they do is they deploy this. This is a test setup here where they mount the helmet on top of a dummy, and they put 2 or 3 of these, maybe more, down in a field. And they put a sniper out in the field somewhere, and they start firing shots, and they fire quite a number. And then they, go through their process of analyzing the results of what the helmet did under various conditions and whatnot. So in this scenario, we're going to have up to 3 different helmets operating in a field, and the sniper is typically going to be down over here, located to the bottom of the page, sort of type thing. But anyway, I'll put the link to this paper in the description of the video. And this paper consists of 2 parts. One is a PDF. Well, it's all PDF, but it consists of 2 parts: a presentation typewritten thing, and then a PowerPoint style set of slides at the end, all presented in a PDF format. So where do we start from here? Well, first off, I better get my little tool up for drawing. And then we can get started with the whole mess. And while I'm at it, I'll make sure I'm recording here. Yeah, we're recording. I use OBS. Alright, so back to this PDF, and our drawing tool will come up eventually. There we go. Alright. So, and during the whole process of this, I like this paper because it has some very clear drawings and some what I consider to be very clear explanations of what they're trying to do. So let me get you to the heading of this, just so I can give credit to the people who are doing this, and I'll leave it there for you to read a little bit while I'm talking. And I'm going to take you through this paper, and I'm going to show you some graphs. I'm going to show you some equations. I'll explain the equations, and I'll explain the graphs. I'll skip over some stuff. I'll pick up some highlights from some of this stuff, all in confirmation of what I've been doing in terms of explaining things, and maybe a little bit different perspective on some of the ways that other people approach the problem who are quote-unquote professionals in the field, and the difficulties they encounter. Now, this system appears to work pretty good in prototype scenarios. I haven't seen a lot of results of the testing in combat situations, because in combat, there's always lots of noise. There's always things flinging around, dirt, grime, lack of communications, all sorts of things that can run amok with and foul up even a good product. Alright, so let's get with it. And I'm going to go back and forth in this paper quite a bit. And let's see, here we go. So now here we're going to talk about detecting a small caliber weapon fire. And what they're talking about here is detecting 2 things: the Mach wave produced by the supersonic projectile, and on the left we see a picture of it. It's taken by Solarian photography. And let's get this. No, let's leave it pretty big. Let's go with green. I like green. So anyway, here you can see the bullet as it travels from right to left, and behind you can see the turbulence left behind, and then you see 2 distinct lines. The first one originates as the bullet pushes through the air and compresses the gases ahead of it, and they spread off around it. And this is this is where you go from the ambient pressure to high pressure, because as the bullet pushes through the gas, it compresses it, creating high pressure. And then all those gases, kind of flow backwards, and then they reach this point because of the nature of the wave being generated at the end here, low pressure. So over here in X, we have lower pressure than here, but the highest pressure is at this front end. And that collectively produces the shock wave. So this is high pressure at the top, and this is low pressure at the bottom, and ambient pressure would be right through the middle. So as the head of the bullet comes through, we generate this massive overpressure, as they call it. And then as it slides by, then it goes from that high pressure to this tail end here, down, and then back up, producing what we commonly call the N wave. Alright, now if you've listened to my stuff at all, you're familiar with this, which is commonly known as the Mach angle. That is, the angle between the turbulence and there is the Mach angle, which can be represented by theta, alpha, or any of the other Greek-speaking letters. Anyway, I don't know why scientists like that stuff, but they do. So anyway, that's what it looks like physically. This is what it would look like on your waveform. And then we drop down. And the thing to note here is that the scale on this is 9 milliseconds. So the width of this is far less than 1 millisecond. In this case, it's probably on the order of, I'm just guessing here, 200 microseconds, or 0.2 milliseconds for the width right here. All right. Now if we drop down to the muzzle blast, we'll see a different picture. This is what comes out of the end of the gun. And the first thing we want to notice is that the scale is different. And this time we're measuring things in seconds. So we go from 3.48 to 3.53, which is, let's see, from 50 to 53, that's 50 milliseconds. Okay, whereas up above, we were talking about tenths of a millisecond. So the muzzle wave is much wider. The distance from there to there is much wider. And because of that width, the frequency is lower. In other words, width determines frequency. So when we come down to our spectral analysis, like I do all the time in Sonic Visualizer, you'll see that the muzzle wave, as depicted here, occurs in the lower frequencies, and the supersonic crack or the shock wave appears in the higher frequencies. Now both of them can contain components of all the frequency ranges typically, but they're at such reduced intensities that they just don't appear much. Alright, moving on. Is there anything else? Well, here they confirm that the muzzle wave has got more energy in lower frequency range than the Mach wave. So that just means that there's, what it is, greater energy in the lower frequency for the muzzle. What I want to do is drop down to, well, they go through a lot of different algorithms in their helmet to make estimates of velocity and caliber and distance, time of arrival, the direction of arrival, and all those things. And to do so, they have to go through some pretty sophisticated algorithms. It's not a simple matter of measuring when the muzzle arrives or when the shock wave arrives. And to get some of the information, they have to have special hardware. And for this helmet, they have two channels. One is sampled at 10 kilohertz, and the other is sampled at greater than 80 kilohertz. And what that means is that you have one low frequency channel and one high frequency channel. Just as a point of reference, your common audio is recorded at 44.1 kilohertz. So the 10 kilohertz channel is much poorer quality for audio than the CDs, and their greater than 80 kilohertz channel is much better than standard audio on commercial grade stuff. And by greater than 80 kilohertz, they probably are going up to 100 and 128 kilohertz. And you have to do that because the sampling rate is inversely proportional to the frequency, and you have to get a small sampling rate to represent these quick moving shock waves. For the muzzle blast, just about any frequency will do, but for those shock waves you have to have a small sampling rate. Alright, and then they talk about how to detect a muzzle or a shock wave and what they do with it. Let's see. So here they say that if they detect a Mach wave, then the following signals are interpreted as a muzzle wave, the second signal anyway. And for this muzzle wave, they apply a special technique for analyzing and looking at it, and they look only in the range of 50 hertz to 500 hertz, which is pretty typical for a small caliber muzzle wave. And they do it by looking at windows in time of 2.5 seconds each, and they grab the average energy from that and then compare it to I'm reading this. They compare it to a smaller region here. Whoa, look at this. Let's see, the time of arrival between the Mach and the muzzle wave for a 14.5 millimeter caliber rifle. 14.5 millimeter, holy Christ. There's 25.4 millimeters to the inch. So 14.5 millimeters is like 0.57 caliber rifle. Oh my God, that's a monster. That's a anti-material range thing. That's a rifle that is taking down elephants for sure, but probably loaded up with large caliber bullets or explosives to take out communications equipment, telephone poles, maybe even some kind of armored personnel devices, etc., etc. So that's a large caliber rifle. They use smaller ones. I didn't realize they used that big a rifle in some of these things. So anyway, and of course, as I've explained before, the larger the caliber, the lower the frequency on the muzzle. Alright, so here we are. Let's get down to some pictures and start explaining things. And I'll come back to these. These are the equations that are used to calculate the propagation characteristics of both the muzzle, in this case the time of arrival for the muzzle wave, and the time of arrival for the Mach wave, as they call it. And as you can see, this is a pretty simple example of one of the various different types of equations that can be used. But before we talk about those equations, and I'll explain them in detail to you so you're not having to interpret them yourself, we've got to take a look at this picture. And in this picture we have a gun located on the left, and it fires a bullet and it travels along a line like that on the green line, and it emits a muzzle wave. Let's just call it muzzle wave, and that muzzle wave propagate. Then the helmet or the observer is located over here at H, and then that muzzle wave just propagates right down that. So the length from S to H divided by the speed of sound would be the time it takes for the muzzle wave to propagate from the gun to the helmet. On the other hand, the time of propagation of the shock wave is going to be the time it takes the bullet to travel to D, and then the time it takes the shock wave, which is created here, to travel from D to H. So you have two components there, and I've explained that quite a bit. And then you ask, well, why D? Why didn't it just go over here to M, and that's where the shock wave, because that's a shorter distance? Well, the shorter the distance, the point at which the shock wave, or which shock wave we hear along the large number of them generated, is determined by the normal to the angle. By normal, I mean the line which is perpendicular to the wavefront. The wavefront right here, which is that sonic cone we've talked about many times, is propagating in this direction. Okay, so it will be the angle of it will be the determining factor. Over time it will propagate out a little bit, out a little bit, out a little bit, out a little bit, out a little bit more, until finally it reaches the H. And the one that did that is the one along the yellow line. It just takes it a while once it leaves D. So it has to be at 90 degrees to the leading edge of that cone. So if we go back and we erase some of that, we can see things a little clearer. We can see that the little red boxes indicate 90 degrees. So the arrival path from D to H is at 90 degrees to the front side of the cone. And that's what determines the path. Alright. And with that, let's go back to the equations above. And I'll drop back and forth down here. Guess I better erase that. Alright. So, the first equation here is the one for the muzzle. And it says literally that the arrival time of the muzzle, that is equal to the time at which we fire it. So let's if we fire it at 10 o'clock p.m., then we'll hear it sometime later by this time t of sh, which is the time that it took this distance right along there from S to H. And as I've explained earlier, the muzzle wave propagates at the speed of sound. It propagates from the end of the gun to the observer. And so all we have to do is calculate the distance from D to H and divide by the speed of sound. Alright, we'll see what the equation says. And it says that to calculate that, we just have to take the absolute value of the length of the path from S to H, and that's all those bars mean, is take the length of and divide it by the speed of sound. So that's simple enough to do. That's just simple geometry. Now, for the shock wave, things aren't quite so simple. It starts out simple. It says that the arrival time of the Mach wave is equal to the time at which the gun was fired, plus the time it takes the bullet to travel from point S to point D, and plus the time it takes the shock wave to travel from D to H. So if we drop back down, that's all copacetic, because we said it's the time if we fire the gun at this time at 10 o'clock at 10 p.m. then the time at which the observer at H, which is the helmet array, hears it, is the time it takes the bullet to travel from S to D, which is the distance from S to D divided by the speed of the bullet, which we'll get into in a minute, plus the time it takes the shock wave to go from created at D to go from D to H, which is the distance from D to H divided by the speed of sound. Now I hope that's not too intimidating at the moment, because the equation is certainly to new users intimidating. But in actuality, it's not that hard. So, for each of these components, we'll look at them. T0 goes to T0, which is easy enough. That's the time at which we fire the gun. And then the time it takes the bullet to go from S to D is this term, and I'll explain that in a moment. And then the time it takes the wave, the shock wave, to propagate from D to H, which, if you remember, is from the bullet path to the observer, is this over here. Now, I express that as I'd usually explain that as the time it takes the shock wave to go from D to H as the length of the path from D to H divided by the speed of sound. But it can also be expressed in terms of this distance, which we call the mist distance. And you've heard me mention that a lot. Mist distance, cross range distance. And to do that, we simply use geometry. Simply, he says, and let's get rid of this stuff here before we go. And we can, if we want to express it in terms of the mist distance, it's the mist distance divided by the speed of sound, c, times the cosine of alpha, alpha being the angle here, and commonly referred to as the Mach angle. Alright, now I'm not going to go through that derivation, but it's pretty straightforward. And since I'm not the one doing this paper, you just have to trust these guys, and they're correct. I mean, so far I haven't seen anything to indicate that this isn't the straight skinny. So we've taken care of this term, and this term is trivial. So what does this term here mean? Well, that's nothing more than a calculation through calculus required to determine the amount of time the bullet goes from point A to point B. If the bullet were traveling at a constant velocity, it would be trivial. It would be the distance divided by the speed of the bullet. But since it isn't, and the speed of the bullet is denoted by v, but since it isn't, the bullet is constantly slowing down, then we use calculus to determine the exact time of arrival of the bullet. Now, we could make lots and lots of approximations for this term initially, because most small caliber weapons in the first 200 yards, maybe even 300 yards, depending upon the caliber of the weapon, travel at a pretty constant velocity. Beyond that, they start to slow down, but for small segments in time, they're pretty constant in velocity. And if you have a and you can just, if you want to travel, say 500 meters, which is a long way for some of the small calibers, you can say it's this constant velocity plus that constant velocity plus each one of these segments. And you can look those up in tables, but rather than doing that, we use calculus to determine precisely what the travel time is. And that's all that this is doing. This is called the integral taken from S, which is where the gun was fired, to D, which is where the shock wave left. This would be D. And so, in this case, we're calculating the time it takes the bullet to go that distance when the velocity of the bullet is not constant. And we'll have to plug in some numbers there based upon, the caliber of the bullet, the load of the bullet, and all those other things to come up with a real number. But we can make some approximations, and they do. Alright. But what I wanted to point out to you here is that using these real equations, these fellows have demonstrated what, it takes me a long time to explain, is that it's not a simple calculation when you're dealing with these shock waves. There's some real math involved, and this is actually one of the simplest of equations involved when you get right down to it. For the shock wave, anyway. Up here for the muzzle blast, that's all fine and dandy. Now, when you get dozens of them together, then you have a whole nother problem completely. But let's move on. I don't want to get into the weeds too much. I just want to point out that this is a pretty good representation graphically of what's going on when you're looking at both the muzzle blast and the shock wave calculations, and this is called the geometric model. Okay. I'm not going to get into that. All this says is that there was this fellow named Whitham who was a mathematician and who published several decades ago a paper describing the shape of the wave created when gases are flowing over objects of fixed and known shape, and what the nature of the shock wave is like. And so I'm going to, because there's a lot of information inside that shock wave that can be garnered about the caliber of the bullet and the speed of the bullet, density of air and all that sort of stuff. But I don't think I want to get into that tonight. So here we have an example of what they're doing with their array and what it calculated, which I find quite interesting. And I find it quite interesting because here we have at this little yellow spot a helmet, and I believe that the sniper is located at this blue area. But what we have is an estimation from the helmet of three things. First we have an estimation of the I'm going to go up here and make sure that I know the line colors. Let's see. Red line, black line, red, black, green, and those are values of the direction of arrival of the muzzle. So the red line is the muzzle, so let's write that in. Muzzle. So the red line here represents the muzzle. We'll just call it MZ, muzzle. The black line represents the direction of arrival of the Mach wave. So let's put that in yellow over here. This is the Mach wave, and then the green represents the bullet trajectory, which is this line. Okay, so the helmet determined that the muzzle wave was coming from the area over this way, as denoted by this line, which all looks fine and good. As you would expect, the muzzle wave comes from a source, it travels line of sight, and it gets to you. Okay, now the Mach wave. The Mach wave this helmet predicts is coming from this direction. Now, as you recall, I've explained this many times, is that the Mach wave having been generated along the path of the bullet, and in this case the green line is very close to the helmet, therefore the Mach wave was generated close to it, and the angle between the helmet and the bullet trajectory is small, and therefore the direction of arrival of the Mach wave is almost perpendicular to the trajectory of the bullet. Not quite, in this case large. Okay, so if I were a person standing there, I get my chart back. I made it, I scrolled it up. I shouldn't have. Okay, the helmet is right here. So a person there wearing that helmet would properly identify the shooter down here from the muzzle wave as being ahead of him, but he would also properly identify the Mach wave as coming from his left, almost at a perpendicular angle. Okay, and that's what makes locating the shooter difficult, is that if you hear the two sounds, then you have to distinguish which is which, and you have to understand that the muzzle will present a true direction to the shooter, but the Mach wave will present a direction that is wildly different often than the actual thing. Now, the further away, the greater the mist distance, the more this angle decreases to where it starts to approximate the shooter's position. All right, so let's erase that. So this is I like their graph here. I like what they're saying, and it's easy for me then to go over it and show you what they're talking about. And I guess I didn't erase everything. There we go. Blue. Got it. Alright, let's move on here. That's not of relevance for us at the moment. End waves I don't want to talk about. Okay, here we come across 3 helmets. Now in this example we see that each helmet predicts the bullet. Now remember, the sniper is somewhere down in here, in this yellow area. And this is helmet A, B, and C. Helmet A says that the muzzle wave came from there, which that's pretty good. Helmet B says the muzzle came from there, but helmet C says muzzle came from there, which is a distance off. And they'll explain to you down there why that was true, and it has to do with the sample rate on the 10 kilohertz channel being used to estimate things which, like the Mach wave, which require a large frequency signal. So that's all. But generally speaking, it was pointed in the direction of arrival, was pointed correctly for the muzzle waves. Now let's talk about the bullet trajectory. Okay, the bullet trajectory for helmet A was projected as this line, which seems to be pretty close. For B, it was this line, and for C, it was, it's kind of hard for me to see even, it was this line, which wasn't so great. Again, that C helmet seems to be off a little bit, but they're all pointing roughly in the right direction. They're just off side to side a little bit. And then if we go back over to the direction of the shock wave, helmet A says, hey, it's coming from over there. B says, hey, it's coming from over there. And C says, hey, it's coming from over there. Well, those are wildly different, but they're all somewhat correct in that the path of the bullet was, kind of like this. So the people on the left will see it coming from the right, or in this case, the people on the left side will see it coming from the right, and the people on the right side will see it coming from the left, because it's coming from the bullet which is between A and B. So that's all good. So it's doing a pretty good job. And as you can see, once again, the direction of arrival of the shock wave is not intuitive. And in my last video, that's what I was trying to say. It's not intuitive. Neither the direction it comes from nor the time it gets there is intuitive. And so you have to be careful when making statements, whereas the muzzle wave is intuitive. Wherever you hear it coming from, that's where the sniper is probably located, unless it's a reflection of some sort. And the time is the straightforward calculation of distance divided by the speed of sound, which you can estimate. If you use an estimate of 1 foot per millisecond, then every second represents 1,000 feet. And that's a good approximation. You can do that quickly in your head. But not so with these shock waves. That's a whole different ballgame. Alright, let's get down. I like pictures tonight. I don't want to go through a lot of equations. Now here's that same scenario, only not same scenario, same number of helmets but set up a little differently, and you can see the same exact thing in that for helmet 1, the missed distance, actually they call it array 3, I don't care what this is the missed distance, this is the angle at which the shock wave was coming from, and this is the angle at which the muzzle, and as you can see with the sniper being here, that all makes sense. And on the other side of the bullet you have array 2 and array 1, both of point for the muzzle, not the muzzle, the shock wave coming from those directions, and that's correct because that does point towards the bullet path. As long as it points towards the bullet path, we're in good shape. And then for both of those, the muzzle wave was there. I know that's kind of a slobby point, and that's correct also. So that's all good. So let's move on to the next picture. And I tell you what, I'm going to leave that on the screen for about 1 minute and go to relieve myself. Be right back. Alright, that'll certainly give me some more time to think about things here. So let's move on to the next picture in this little thing. And as you can see here, they're trying to say that, you know, with one helmet or two helmets or three helmets and they're all on one side of the bullet, you know, the estimates can be a little off. And this is just saying this is how they calculate the best solution, shall we say. And they do it by taking the missed distances and multiplying them by themselves. That's called the square. And then they add them together and take the square root to get an estimate. And they do that many times, and then they take the smallest ones. So that's what they call minimizing the quadratic error. You know, it's a big long equation here, but in reality it's a simple calculation. Alright. So then they go into, and that's where we started with this little paper, they go into analyzing the results and making proposals about how they can improve it. And here they provide their results, which are actually quite good. First they give you helmet A, helmet B, helmet C all operating independently, and then they give you the three helmets connected together in a network and the results. And in the case of the helmets, they fired 695 shots each. They had no false representation. They had no undetected shots. And they had two undetected or badly detected muzzle waves. Okay, for those two. And then helmet C, which had a slight problem, had one undetected shot. So now when they were networked together, it actually got a little worse, and I'm not sure why. Alright. Now, this is kind of interesting. Yeah, I don't want to go into why that was bad. Let's just go down to other pictures which I find interesting. And these are the PowerPoint slides. And I'm going to go through and high grade this. Here they're kind of overlaying the Whitman equations on top of the shock wave, showing you some of the relevant pieces of it. I'm not prepared to get into that tonight. We've seen that one. They had a graphic. Yeah, that's a hell of a muzzle blast right there. Yeah, I don't think we saw any of that in Vegas. Oh yeah, this one I like. This is a real good one. In French, of course, because they're French. I want to go back to green. I like green. In this case, what we have is a shock wave that's high amplitude. Then we have probably a ground reflection here, immediately following it. And then sometime later we had this itsy bitsy little tiny blip on the radar, barely visible, called the muzzle wave. Now in this case that means, to me anyway, let's see, 1, 2, 3, 4. So we're talking, that's in seconds obviously, so we're talking close to 1.5 seconds. So that's got to be at greater than 500 yards, depending upon the caliber of the weapon. But as you can see, at great distances, where you're recording close to the trajectory of the bullet, you get a strong Mach wave, a good strong reflection, and then little or no muzzle wave. So it is possible at large distances that the muzzle wave is not recorded, even if you're close to the trajectory of the bullet, and the trajectory of the bullet being close will generate a loud Mach wave. And that's what this is saying. So let's erase our doodling and move on down to the next graph or picture, whichever you want. Let's see. We're not going to talk about that stuff. Here they're talking about how they had trouble initially in their system where it would detect sounds going by from cars, which is what that is and this is, or artillery or other things, as false positives. And they had to develop an algorithm to eliminate that stuff. And what they did was they took the signal and measured it over 2.5 second windows, and they averaged the energy. Okay, so in these regions you'll see that the energy is kind of low, and these in the regions where you have background noise, it's a little bit higher. And then they took, that would be the average energy on a 2.5 second sliding window, and then they took a much smaller window to try to capture the waves, and then they took that energy and compared it to the background energy and made a distinction, and that improved their isolation detection and reduction of false positives substantially. And that's all it's saying. So as you can see, trying to determine what is or is not a muzzle wave or a shock wave can sometimes be problematic, because even these say a small signal right there could look like one of these bigger ones, only shrunk down. So you'd have to know how big that energy is and what it is, kinda, to eliminate that spike as a potential gunshot sound. And that's what the algorithm was trying to do, because we can conclude here that if there's this type of energy over this period of time, then this spike is most probably associated with that, and you can do spectral analysis on it, i.e. frequency and energy, width of the pulse, and all that stuff to eliminate it. But on the other hand, you may be eliminating a deeply buried signal, and that's the risk you run. So yeah, you see these are at 1,000 meters. At 1,000 meters they must have been using a 50 cal And here they were measuring energy in the frequency range of 80 to 500 hertz, which means they'll be measuring I don't know, first wave. That should be the I don't know what they're doing there. But as you can see, the signal to noise ratio is not that great. Alright. Blah, 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 blah. And I'm not going to go into that, that's for sure. And here they go into time of arrivals, time of arrival, helmet C. Yeah, they're getting into the nitty-gritties here, which I don't think we really need to get into tonight. And there's up close of the helmet, what it looks like. And I'm not sure where all the sensors are embedded. Okay, very good. So that concludes an overview of this helmet. And the takeaways from this are the things that I've been trying to pass along to everyone is that, oh, here's a bibliography. It's not very extensive, but it's good stuff. Let's see, do they have reference to the Whitman in there? Nope. Okay. What they conclude in this is that they have work to do. That they'll have to resort to some more sophisticated algorithms to completely make this thing usable. Alright. Is there anything I missed? No, I think I pretty much caught it all. So let's go back and summarize the takeaways from this. One is that doing stuff with the shockwave is hard and involves non-trivial math. Trying to measure these shock waves is difficult because they're such short duration that you have to have high frequency sampling to make accurate measurements. We don't. All we have is the commercial stuff. Okay. What this paper doesn't discuss a lot is the background noise, except to discuss artillery or carrier type stuff going by. In our case, almost every video is dominated by the non-gunshot acoustics, people screaming, cars, sirens, running, rocks, motors, you name it. So it's a much noisier environment, and there has to be, if they were to use these helmets in the venue, I'm sure that they'd have to make substantial improvements to their algorithms to do a good job of detecting some of the sounds in some of the situations. But what I want to get back to the takeaways here. The takeaways is that it's a difficult job detecting, one or two signals out of all the noise, particularly if those signals are just the shock waves, is tricky. Now, if you have hundreds or thousands of them, it becomes much easier, and that's what we have for most of the rounds. Is we've got 1,000 of them, and I can look at all those shock waves, and I can measure those 1,000 shock waves on 50 videos. Not all of them cover every shock wave, and so I don't have to rely upon one or two or three or four or five measurements. And in this paper, they go on to explain how, with just 5 measurements of shock waves, it can be tricky unless you have good, high-quality sampling that can accurately characterize the N wave from the shock wave. So that's one takeaway. So when I'm looking for these sniper shots, as I've been doing in the last couple of videos, you have to understand that this isn't intuitive. It's not like the muzzle wave, where you can say, the louder it is, the closer you are. Typically, the first one to hear it is probably the closest to the shooter's location. The shock waves don't work that way. They come from different angles. They come at different times, and it's non-intuitive. And the sampling rate of the commercial devices isn't high enough to accurately characterize the N wave, and if you only have 1, 2, or 3 of them, man, that's a tough job, particularly if it's just the shock wave, which is what we've been looking at most recently. Now for muzzle waves, you give me 3 of them and I'll tell you, reasonably in a rough direction where the shot came from, but not so with those shock waves. And this paper only discusses a couple of the well-accepted approaches to analyzing shock waves, and for that matter, muzzle waves. All right, well, that's enough of the weeds tonight. I hope this little explanation helps. I'll put a link to this in the descriptions for those who are brave and hardy and interested. And we'll grab you in the next one.